Okay, my name is Greg Hillhouse, and I'll be chairing the session. For those of you who do not know me, I'm head of the Department of Physics and Astronomy at the Botswana International University of Science and Technology, BUST. We are looking forward to the exciting talk by Dr. Adrian Taplady, entitled Search for the Origins of the Universe, the Story of the SKA. Before we start, may I kindly request that you mute your microphone until the end of the presentation. The structure of the session will be as follows. Our esteemed Vice Chancellor, Professor Totolo, will give some welcoming remarks. Then after that, I will introduce the speaker, and then Adrian Taplady will give his presentation. This will be followed by questions and answers. And then right at the end, our Permanent Secretary, Professor Toto, will give closing remarks. So without further ado, I'd like to invite Professor Totolo to say a few words of welcome. Over to you, Prof.
Thank you very much, Professor Hillhouse. You have already gone through the list of protocol, so I will not mention everyone because you have already done that. But let me recognize the Permanent Secretary. The Permanent Secretary in the Ministry of Tertiary Education, Research, Science and Technology, Professor Nelson Toto, the Deputy Managing Director, Strategy and Partnerships at the South African Radio Astronomy Observatory, and also the guest speaker for tonight, Dr. Adrian Taplady, the Deputy Permanent Secretary, Dr. Obakeng in the Ministry of Transport and Communications, Professor Modise, Director of Ceremonies for today's webinar, Head of Physics and Astronomy at BUST, Professor Gregory Hillhouse. But let me just say all protocol observed, and I welcome you to this meeting. Kapula. Kapula. It is my singular honor and privilege to welcome you all to this special virtual session hosted by BUST. Let me, by extension, welcome the international audience here present to the beautiful Republic of Botswana. I'm speaking to you from Palape, a town 270 kilometers north of the capital city, Gaborone, along the main A1 road towards the second city of Francistown, that is close to the prestigious Botswana International University of Science and Technology. I wish to extend a special welcome to the Deputy Managing Director, Strategy and Partnerships at the South African Radio Astronomy Observatory, Dr. Adrian Taplady, and thank him for honoring our invite to speak today on the topic, Research for the Origins of the Universe, the History of the Square Kilometer Array. SARAO is a critical stakeholder and technical partner in the rollout of the African Very Long Baseline Interferometry Network, AVN, and the Square Kilometer Array, SKA project. Your presentation this evening, Dr. Taplady, is a clear testimony of the strong relations that exist between your country, the Republic of South Africa, and Botswana that has persisted for decades. The Botswana International University of Science and Technology is the country's premier center for research and innovation, with space science and technology development at the core of our strategic intent. In the current strategy that ran from 2016 to 2022 that is due for review, we see ourselves as a catalyst for innovation and transformation. Directorial ceremonies, we are delighted as BIOST to have been nominated as the host institution and to lead the coordination and collaboration of SKA activities in Botswana by the Ministry of Tertiary Education, Research, Science and Technology. Let me share with you that BIOST executive management team has sanctioned a development plan for astronomy and planetary science for the next 5 years. That will see the institution have the following flagship projects: AVN radio telescope, National Optical Observatory featuring a planetarium, Planetary Science Center of Excellence, and hosting of the outliers for the hydrogen intensity real-time analysis experiment, HIREX. As a way of update, let me share with you that the AVN radio telescope project is well underway, with the government of Botswana having committed funding for the infrastructure provision for the site for the 2020-2021 financial year. Thank you, government of Botswana, represented by our permanent secretary, Professor Toto, and of course, Dr. Obakin. The site surveys are being carried out for radio frequency interference characterization, geotechnical, floodline analysis, and hydrogeology analysis. The AVN SKA projects are a multi-sectoral project that BIOST is jointly implementing with other collaborators, including the University of Botswana, Botswana Institute of Technology, Research and Innovation, Botswana Geoscience Institute, Botswana University of Agriculture and Natural Resources, Botswana Communications Regulatory Authority, BOCRA, Botswana Fire Networks, BOFINET, Astronomical Society of Botswana, and others for the success of the project. We cannot do it alone. We need to work collaboratively with others. There are synergies and strengths and experiences residing in the institutions that I've mentioned, Mr. Chairman. And we believe for us to succeed, we must work hand in glove with them for the success of this very, very important project in our country based at BIOST. Ladies and gentlemen, active involvement in space science and technology has many benefits for any nation. It leads to greater security, safety, and agricultural productivity across a broad front of activities, drives the development of capabilities in high technology, creating jobs in those areas, and exercise the young people to pursue studies and later careers in science, technology, and engineering and mathematics, STEM. Dr. Tip Lady, talking about the magnificent MeerKAT dishes that your institution has built as a precursor to the SKA. I must say that I've personally been to the facility, and it is a marvel to learn about the scientific explorations and the limitless opportunities that science can offer. With these few remarks, let me take this opportunity to once again welcome Dr. Adrian Tiplady and it is always a pleasure to listen to what the square kilometer array promises. I thank you, Baretsu. Kapula.
Thank you very much, Prof. Totolo, and we thank you for your support. Colleagues, several people are joining. I'm very happy. We have people from all over the world, especially we have from South Africa, other University of Botswana, even from Israel. So welcome, colleagues. So it's now my pleasure to introduce Adrian Toplady. Bumped into him in several times in South Africa, but he's a very busy guy, so we're very lucky to have him here. So I'll just read briefly his biography, which most people should have received. But Adrian is currently the Deputy Managing Director of Strategy and Partnerships at the South African Radio Astronomy Observatory. He holds a PhD in astronomy with specialization in radio pulsars, or some of us call it neutron stars in theoretical physics, with an honors degree in telecommunications, a bachelor's degree in physics and electronics, computer science, and musicology. And, that's an interesting one, and maybe there'll be a question about that, and compositional techniques. Adrian joined the South African SKA project, as it was known back in 2005, as an assistant project scientist, and he's held a number of very diverse roles, from very technical field of radio frequency interference engineering to broader management roles in strategic planning and risk management. He was also involved in the preparation of Africa's 2012 successful bid to host the SKA, and he was involved in the establishment of the legally protected radio astronomy advantage area in the Karoo, which I've been lucky enough to visit. And he's also very much involved in working closely with the South African Department of Science and Innovation in the establishment of the SKA Intergovernmental Treaty Organization. So Adrian is actively involved in many spheres. He's a member of the European Science Foundation Expert College of Reviewers, the European Expert Committee on Radio Astronomy Frequencies, International Scientific Committee on the Allocation of Frequencies for Radio Astronomy and Space Science, and he's currently involved in the development of a national open science policy in South Africa. So, Adrian, welcome. We really hope one day you will visit Botswana. You know, Botswana is famous for its beef, safety, good governance. It's a very, very different country from any other place on the African continent. And we look forward to having you here one day. So with that, I'll hand over to you, Adrian.
Thank you, Greg, and it's indeed an honor and a privilege to be invited to speak this evening. And I have indeed had the privilege of visiting Botswana during my travels, and specifically engaging on matters of radio astronomy and the SKA project. So I certainly hope to get back there soon. And I must admit, I'm a lot more used to giving presentations and physically and engaging with the audience. I guess you know, one of the aspects of COVID these days is we get less opportunities to do that. But on the positive side, I think it's provided wonderful opportunities to be able to have these kinds of engagements and have people joining from around the world, as you said. So you know, really I'm very happy and pleased to be able to get this opportunity to speak about the SKA. And just as a brief introduction, you know, the South African Radio Astronomy Observatory in South Africa it's been responsible for implementing South Africa's strategic investments in radio astronomy. It's historically operated the Hartbeespoort Radio Astronomy Observatory near Johannesburg, and obviously more recently become involved in the SKA project and the construction of the MeerKAT radio telescope. And let me just, I hope I can get this right, because there we go. And those of you who've perhaps seen me speak before, I really tend to use this slide to almost start off all of my presentations. And I think the reason why is because it it really tells a story of how much more there is to learn and understand about the laws of nature and the laws of physics. You know, a number of decades ago, scientists really thought they understood how the universe evolved, the laws of nature and the laws of physics. And a few very simple experiments were undertaken, which really shrunk everything we knew, the whole energy of the universe, everything that we can see, everything we can touch, the heat of the universe. You know, it really shrunk everything into something like 4% of the total energy content of the universe. The rest of it was made up of, or 21% was made up of what we refer to as dark matter. And for those non-astronomers out there, dark matter is really like a glue that holds galaxies together. If you can imagine, I like to imagine a frisbee and dribbling some grains of rice onto this frisbee. And as I spin the frisbee around, I expect to see these grains of rice go flying off the edge of the frisbee. And I expect to see that when I look at stars and the galaxies, and as the galaxies are turning, I expect to see the stars spread out and spin off like the grains of rice, but they don't. It's almost as if someone took some glue and stuck the grains of rice on the frisbee. So it's just this glue which is holding these galaxies together, and that's what we see at night with these galaxies as they're turning around. We can't see it, and so you know, for some reasons, it's called dark matter. The rest of the energy content of the universe, about 75%, is made up of this stuff called dark energy, which is almost an anti-gravity. It's causing the universe to expand, but expand at an ever accelerating rate. And it's discoveries like this and questions like this which really make us ask, you know, do we really understand the laws of nature? Do we understand the universe? Do we understand how the stars and galaxies were formed? And to answer some of these questions, we need to think about the kinds of scientific instruments and the research infrastructure that we need to build in order to try to probe and investigate these mysteries. And so a number of decades ago, perhaps in the early 90s, a group of astronomers really started thinking about that next generation facility. What kind of instrument is required to answer some of these very fundamental questions? And over the years, that grew into the concept of the square kilometer array. What is the SKA? Well, many of you will be familiar with the whole bid process that was undertaken in 2012. It was announced that Africa, along with Australia, would co-host the square kilometer array. In Africa, it consists in its broader long-term vision up to something like 2,500 to 3,000 radio telescopes distributed across 9 countries in Africa, including South Africa, Botswana, Namibia, Zambia, Mozambique, Madagascar, Mauritius, Kenya, and Ghana. Whereas in Australia, in Western Australia specifically, would be hosting, I must say, what I call tongue-in-cheek tent poles in the ground, but they're an aperture array operating a different part of the radio frequency spectrum. And what they're trying to do is really try to probe the understanding of the birth of the first stars and first galaxies in the universe. But it's a lot more about a telescope in Africa and a telescope in Australia. It really is a global endeavor. The global headquarters for the Square Kilometre Array project is located just outside of Manchester at what is the well-known Jodrell Bank Radio Observatory in the United Kingdom. Over 1,000 scientists and engineers have been involved from 20 countries already in developing that detailed design and developing many of the technologies that will be needed in order for the SKA to actually work. And just recently this year was a major milestone. The SKA Observatory was launched as an intergovernmental organization in January of 2021. And it's really only the second intergovernmental organization to have been established dedicated to the astronomical endeavor following ESO. And this is such a major instrument in its grandest vision, something like 100 times more powerful, more sensitive, more technologically advanced than anything that had been built in history, that it really is now designed as a phased deployment, with the first phase of construction perhaps amounting to something like 1 billion euros, with construction due to commence later this year and proceeding until about 2027, 2028. But that's not to forget that the grand vision of the SKA is this large deployment of SKA of radio telescopes throughout the continent of Africa, and really establishing, I think, major global scientific infrastructure on the African continent. Now, in order to answer some of these many fundamental questions, what we really need to do is build a next generation radio astronomy facility. And one of the interesting things about the vision of the SKA is that it's almost premised on the availability of future technology. And what I mean by that is, in many cases, when one is building a radio telescope, they've decided, well, we can't build it today because we don't have the computing power in order to process the huge amounts of data that the telescope will generate. And so what we do is we design the instrument for the kinds of technology that will be available in 5, 10, 15, 20 years in time. Because really what you don't want to do, and I often use this example in a joking manner, but what you really don't want to happen is someone walking into your big new giant supercomputer that you've been designing and building for the last 20 years, and they take out their latest iPhone 200S or something like that and say, well, I can do everything you're doing on my phone. So it really almost is a future-proof kind of instrument. And you'll see a couple of facts on the right of the slide here, which kind of give you a sense of the amount of data and the amount of computing and processing power that will be required in order to process the huge amounts of data coming off the SKA. I mean, every year the volume of data stored by the SKA would fill over 1,500,000 gigabyte laptops. So it's really pushing the frontiers of technology. It's solving key technology challenges in things such as big data, supercomputing, data storage, and distribution. And all of these technologies and all of the skills that are being developed around the development of these technologies are extremely relevant for things such as the fourth industrial revolution, for example. The SKA1, as I said, was going to generate something like 130 to 300 petabytes of information every year, something that is rather unheard of in today's standards. It will be developing complex data processing and machine learning techniques. And as I say, it really is a next generation technology instrument. So what are we going to do with all the technology? Well, we're going to do science. We're going to do fundamental science. We're going to be solving some fundamental grand scientific challenges, understanding the birth of the first stars and galaxies of the universe, testing whether was Einstein correct or not, testing general relativity, searching for potential signs of life, understanding the role of magnetism throughout the universe, the exploration of the unknown. I think radio telescopes, in fact, many radio telescopes around the world it's probably true to say that they are famous not for the purposes they were built, but rather for what they serendipitously discovered afterwards. And I think that's a very key take-home message. We can design the SKA today and have huge science cases, and in fact, much of the science case is actually written in these two rather large volumes. I think a number of scientists, hundreds of scientists around the world contributed to this development of these two volumes, which forms the basis of the science case of the SKA. I'm told it weighs something like 4 kilograms. So it is quite a encyclopedic coverage of the type of science that the SKA will do. But I think what we'll probably discover afterwards, that we had no idea what we would discover, that we had no idea that we would discover it, is probably going to really make the SKA one of the great scientific instruments of the future. Now, one often asks the question, and I think the comments were made earlier about the benefit. What is it that something like the establishment of basic research infrastructure, and the establishment of a radio astronomy and a huge radio telescope in Africa, what benefits does it bring to Africa? And this is a model that we've been working on for the last couple months, which is really a generic model that can be applicable to investment in any kind of research infrastructure, but I think it's hugely applicable to investment in things like radio astronomy and the SKA project. It really is two components, and really what it's saying is that, you know, there are two types of value propositions that are posed by investment in something like a radio astronomy. First is, what does Africa offer to the world in respect of hosting of a huge instrument such as the SKA? And I think there are a variety of things here. There's certainly a strategic geographic advantage, and what I mean by that, in the case of radio astronomy, Africa is an extremely large continent. There are places which are very sparsely populated. Sparsely populated areas means dark and radio quiet skies. The perfect kind of place to build an astronomical facility. And these kinds of places are becoming more and more hard to find around the world. As we build more and more sensitive radio telescopes, we need to be able to build them in locations that are particularly radio quiet, so that we get as much science out of the instrument as possible. But there are other things such as the demographic dividend, right? So Africa has a young growing population. We have youth that can enter into careers of science, engineering, technology, and start to participate in many of the challenges posed by building the SKA, and therefore set themselves up and be ready for things such as the fourth industrial revolution. So these are kind of very critical skills that are being developed, and I think it poses a huge opportunity for the African continent to invest in basic research infrastructure such as the SKA. But then one also needs to look at what the local value proposition is. Firstly, it's obviously an opportunity to participate and utilize really global research infrastructure, world-class infrastructure on the continent. It provides opportunities for increased scientific output, but also importantly for human capital and research capacity development. Astronomy is the kind of science that really excites the mind and excites the youth, and really draws them into careers of science, technology, engineering, and mathematics, those kind of STEM careers in STEM areas. So it really has that power to do that. And we've seen that quite a bit already around the SKA project. Investment in the SKA is a catalyst for growth of a knowledge economy. And it could potentially also be a model for mission-driven innovation. And here's just an example of what I was referring to earlier about that strategic advantage that Africa has. And this is a population density map of Southern Africa. And you can see certainly, and in fact, even better in Botswana, the population density in some areas is extremely low, which makes for excellent locations for building of astronomical facilities. And I mentioned earlier that, you know, the SKA was this next generation facility, something like between 50 and 100 times more powerful, more sensitive, more technologically advanced, and had been built in history. And what the South African government decided to do is, well, we will propose and develop what we call the Karoo Array telescope, which later became MeerKAT, as a precursor to the SKA. And a precursor, you could say, is perhaps what 5% of the size of the SKA. But when the SKA is 100 times bigger and better, then even the precursor instrument becomes a premier radio astronomy facility in its own right until the construction of the SKA. And through this project, what we've been able to do is establish the Karoo site, as well as establish, importantly, a critical mass of highly skilled expert scientists and engineers. We've established engineering processes that would be critical for the delivery of something like the SKA, because the SKA project is being delivered in a way that no other radio telescope necessarily has been delivered before. And it also delivered a really diversified local value proposition in South Africa. So in establishing that site, we put up power lines. It really was in the middle of nowhere. We've built roads, we established support base, we built power lines because there was no power line infrastructure there. And this is quite interesting. When you're building an extremely sensitive radio telescope, even building a power line is not the standard technique or the standard process, because what we needed to do is build a spark-free power line, a power line that doesn't spark and therefore produce radio interference for the radio telescope and corrupt our scientific observations. And so even the engineering around that was really quite sophisticated, and it really is a one-of-a-kind power line that's been developed for our MeerKAT site. There's a picture of our on-site facility. It's called the Losberg on-site facility. A lot of the magic actually happens in an underground processing facility, which you can't see, but here's a nice view of that underground shielded room before it got filled with computing equipment. When you're building something like a radio telescope, it's extremely sensitive to radio interference. The reason for us building a spark-free power line, but also the reason for us building an underground shielded bunker to put all of that supercomputing equipment that we needed to process the huge amounts of data that are going to come off the MeerKAT, and then one day off the SKA mid radio telescope. This is just a brief picture. Some of you may have seen this instrument before. This is Cat 7. So even before we built MeerKAT, we've never built a radio telescope in South Africa before. So we started off by building a prototype called Cat 7. And really what this did is it's really tested and developed the very strong engineering and system engineering processes we applied. And we want to apply, and we applied for MeerKAT and applying for the construction of the SKA. It's really in the developing of the Cat 7 radio telescope that we refined this. And really it was a remarkable instrument because a lot of work went into it. There was a lot of perhaps some skepticism in terms of how quickly we would be able to build the radio telescope, having never built a radio telescope like this before in South Africa. But I put there in the bullet point there, really it worked first time. We turned the power switch on and it really started working. So it was a really great success story, and we learned a lot about it. The MeerKAT, it provided an opportunity to develop some of the expertise in South Africa, and in fact we like to say that the MeerKAT was locally developed, but of course we learned a lot from our international scientists and international engineers and collaborators, but really there's a huge amount of localization that went into the MeerKAT radio telescope. And so through that, we've been able to establish the competency and the critical mass in South Africa. And here's just a picture of the first reflectors going out and a first complete MeerKAT radio telescope. And just to give you a sense of scale, here's a picture of that telescope with a man standing underneath, shining a torch into the sky. So some of the highlights, so the MeerKAT radio telescope was launched in 2018, and it really has better than promised performance, and I think this is as a result of the really superb engineering that was undertaken by our team, by local industry partners. It was delivered on time and to budget, and it's already attracted further international investment to extend MeerKAT, which is currently 64 dishes, by a further 20 dishes. So it's attracted investment from both the Max Planck Institute in Germany, as well as ENAF in Italy. And the success of the MeerKAT is such that eventually it will be integrated with the SKA mid radio telescope and form the first, it will form 30% of the mid telescope. This is a really quite a glorious picture of what the MeerKAT radio telescope looks like today. You can't see all of the dishes there because although a large majority of the dishes are concentrated in a 1 kilometer core, we do have dishes that are spread out approximately over about 8 kilometers in the Karoo. So what's MeerKAT been doing? Well, when we started off building MeerKAT, we really wanted to understand, will it be relevant for the global scientific community? We issued a call for proposals in 2010, and this resulted in 10 approved large science projects. But by 2016, MeerKAT was perhaps looking like a different instrument than what was promised in 2009. One area, for example, is that it certainly had more sensitivity. And so we refined those key science experiments, and which have recently started commence. I think all 8 LSPs have now commenced their scientific observations. And the telescope has been operational since 2018. 2/3 of that telescope time is used by those large key science programs. 5% of the time is director's time. The rest is awarded through periodic reviews, and periodic calls, and anyone can respond to those calls for open time. So in 2019, we issued our first open time call. And in more recently, we've had a second call for 1,000 hours. And approximately 113 proposals were received requesting 3,400 hours, which means MeerKAT at this time is really an oversubscribed instrument, which is really good. What it means is that it's relevant, and it's relevant for the global science community, and it's relevant for answering many of the fundamental scientific and astronomical questions that remain to be answered. And many of the data sets that have been developed and generated from MeerKAT are now freely available. And I can certainly provide Professor Hillhouse details about how to access all of that data. So this was, I guess, the commissioning image for the MeerKAT radio telescope. And for those of you who were fortunate enough to be at the MeerKAT launch, there was quite a large banner that was printed with this image on. And it's appeared in a number of photos with various dignitaries around South Africa. But it really is just a fantastic image. It was a commissioning image really meant to show off the size and the scale and the performance of the MeerKAT telescope. But there really is some excellent science coming out of this image. It's one of the clearest images, if not the clearest image that's ever been made of the center of our Milky Way galaxy. And it's resulted in really some remarkable science and remarkable publications. This is one of the very first, in fact, the first MeerKAT paper that was published in September 2019. And you notice my background image has the same picture here, announcing the discovery of these huge bubbles that extend out of the center of the Milky Way galaxy. And really just a fantastic and beautiful image to look at. We've been able to solve a number of mysteries, such as these strange X-shaped galaxies. And we've also discovered new mysteries, like these collimated threads in this wonderful galaxy over here. Here's a nice bigger picture. So far, we've had more than 50 scientific articles that have been published using MeerKAT data. I think that number is probably a bit higher. I think it's closer to the last number I saw was about 66. And so there's now real science being developed and generated out of MeerKAT observations. A couple of other examples: discovery of missing hydrogen gas, extremely high precision pulsar timing, which is an area of my area of specialization, setting a new world record in terms of timing resolution. So that's a bit of the science, but I spoke earlier about this value proposition. What is it that Africa gets out of investment in basic research infrastructure, such as a radio astronomy facility? And I think there are a couple of areas, and I'm going to touch on and give a couple of examples here. The first is it provides an opportunity for development of homegrown technologies and commercialization. For the MeerKAT telescope, we effectively delivered the 75th fastest supercomputer in the world, which was designed and deployed by Soraya at 30% of the commercial cost. There's substantial cost savings in the operation of the supercomputing infrastructure because we adopt open source software and we're not really paying substantial amounts in commercial license fees. We're developing techniques and advanced skills to be able to process huge amounts of data every day. You'll recall I mentioned earlier about many of the skills that are developed are very pertinent for next generation needs, answering some of the more fundamental problems, socioeconomic problems that these skills can be applied to. So we've got a bit of an IP portfolio, and we've developed a number of products. One of the most interesting products, and has probably the most is the closest to becoming a marketable product, is something called COMRAD, which is a passive radar system. What it does is it's able to track aircraft in the area without having a radar firing radio signals to bounce off these aircraft, but instead uses the radio frequency environment around us, the natural radio frequency environments. Broadcasting signals from radio stations, for example, are used. So it really is a fantastic piece of technology that's really come out of the development of things such as the MeerKAT telescope. We support other agencies within South Africa, so the South African National Space Agency. We deployed something called a data cube, which is there to process and store Earth observation data products. So I've spoken about skills development, and I think the important thing about something like radio astronomy and investment in radio astronomy has been the development of really critical and expert skills that are highly transferable. And what I mean by that is that many of these skills are able to unexpectedly or expectedly respond to critical or unexpected challenges. And I think the most recent being that of COVID. And I've participated in a large number of workshops, reports that start to look at how global research infrastructure has responded to the COVID-19 pandemic. And I'm going to just take the example, in South Africa, we have two real fundamental basic research communities being able to positively contribute and respond to the national needs to address the COVID pandemic in South Africa and globally. The first is the particle physics community, where they participated in modeling of COVID-19 infections across South Africa. And the second is radio astronomy, and specifically the South African Radio Astronomy Observatory, which was mandated to manage the design, development, and delivery of ventilators for COVID patients, because ventilators, standard ventilators, are extremely expensive, and given the number of COVID patients that were starting to encumber health system in South Africa, there was a dire need to be able to deliver cost-effective ventilators that would be efficient in treating the disease. And so here on the right are just two pictures of the two types of ventilators that were delivered. So Soraya was appointed by the minister to coordinate this project and manage the design, manufacture, and delivery of 20,000 ventilators in response to the COVID-19 pandemic. And this happened as a result of the really Soraya's history and track record of being able to deliver high-tech projects to on time, to budget, and within scope. We started the program in around April of 2020 and completed it in November of 2020, which is a really, really short time scale. We applied a really rigorous system engineering and quality assurance methodologies, and all of these methods were really developed and refined during our MeerKAT project. And we applied that to developing the requirements, specifications, procurement, contract management, the whole lot, all the way up to deployment. And what we effectively delivered was high efficacy treatment systems at a low cost, approximately 12,500 Rand per ventilator. So it's about 750 euros. I think that's, if I try to think of, I think it's about 10,000 pula per ventilator. And forgive my rather poorly drawn arrow here, but it really just gives you an idea of the entire process that we took from the beginning, from really, documents and developing user requirements, etc., all the way through to the final delivered product. And we included, there's prototyping, we included industry that, for example, had no experience in manufacturing medical equipment, but because of the process, because of the whole process, we were able to utilize the skills and expertise that much of the industry had in South Africa and apply it to address this real national emergency. I think human capital development forms a real critical pillar to the success of radio astronomy investments and development of basic research infrastructure. And we started and established a human capital development program back in 2005. And the intention was really to grow a diverse and sustainable research community that would be able to take advantage of both the MeerKAT as well as the SKA radio telescope, and not just the scientific participation, but also the technical participation. And so this program really supports scientists, it supports engineers, it supports artisans and technicians, a whole breadth of skills and competencies that are required for building and operating, and actually scientifically operating and maintaining and utilizing something like a radio astronomy facility. And over something like 1,166 grants and scholarships have been awarded. We've established a technical training center near the MeerKAT site in the town of Carnarvon, which is about 80 kilometers from MeerKAT site. And it covers a broad range of skills that the local community is participating in this training. And these, you can see these are quite generic skills. They really refined and developed for building and maintaining a radio telescope, but also they are clearly applicable to industry that requires it beyond radio astronomy. For example, in South Africa, and particularly in the Northern Cape province of South Africa, which is where the Central Karoo region is located, site of the MeerKAT telescope, there's quite a large renewable energy program, development of wind and solar power facilities. And so, establishing this artisan training center in Carnarvon also provides opportunities for local communities to train up and become available for operations and maintenance of that kind of infrastructure as well. We have a schools program where really what we want to do is we want to ensure that the local community is participating at a meaningful level in the establishment of the MeerKAT and the SKA project. And so we support local schools and in maths and science programs, summer camps, teachers. I believe that certainly the local schools had no qualified maths and science teachers or insufficient qualified maths and science teachers for many years. And Soraya actually supports one of the schools, Carnarvon High School, with qualified maths and science teachers. We've introduced robotics programs at 5 schools in the area. In fact, we're very, very proud to say that one of the teams from Carnarvon High School won the 2019 International Lego Robotics Competition in Uruguay. So it's really amazing. It's testament to the fact that when you give schools and you give the youth the opportunity to excel, they really do excel. And in this case, they've really excelled on the international stage. So it was really quite a proud moment. And of course, we provide support not only to South Africans, but also to students coming from our African partner countries and across the African continent. And we've had a number of students join our human capital development program from Botswana, and we keep track of alumni, and many of them are engaging in further studies, both in South Africa and abroad. One of the other programs we drive is what is called the Development of Africa through Radio Astronomy, or DARA, and that's done in partnership with the Newton Fund in the United Kingdom, and we run DARA and DARA Big Data schools. And over the last 4 years, something like 147 students have participated. In fact, 47 coming from Botswana, which is absolutely fantastic. And I think one of those students is currently pursuing her PhD, which is fantastic news. And as part of the DARA program, which is really fundamental radio astronomy, learning how to use and operate radio telescopes, something like 20 students from Botswana have participated over 4 years. And the program is really seen as hugely successful, not just by us and by participants, but by independent reviews as well. So it undergoes an independent external reviews, and really seen as a fantastic model for human capital development, and really supporting the development of next generation skills. And sometimes I like to say, it's new skills for new jobs, and that's what we're able to facilitate and provide that enabling environment for. Of course, there are a large number of local benefits that arise from construction of research infrastructure, and really our focus is around youth and education, community development, enterprise development, and local empowerment, skills training. And there've been a number of successes. We've established local community knowledge centers, Artisan Training Institute, I've mentioned, a creative crafts initiative where we've trained up local artists. And we find in South Africa, specifically in these kind of Karoo environments, there's a huge amount of talent and creativity in these small towns. And just by going in there, we've been able to tap into this talent and provide opportunities for some of these local craftspeople to sell their wares, expose their wares. And some of them are even now selling their wares in the metropolitan areas, which has been a really fantastic news and fantastic success stories. Of course, we're not here by ourselves, and we rely a huge amount on collaboration both with institutions in South Africa as well as internationally, across the world. When we began the entire project, we really had a lot to learn about how to build a radio telescope. But really what the goal and the intention, the strategy around this was learn what everyone else knows about building radio telescopes, and then try to take it one step further. Because what we really needed to do is develop new techniques and new methodologies to enable us to design and build the SKA radio telescope. Here's just a very brief snapshot of the kinds of collaborations that we have. Max Planck Institute for Radio Astronomy, who invested in MeerKAT through delivering S-band receivers. All the instrumentation, the back-end instrumentation, is not just developed and delivered by South Africans. It's participation. There's global interest in the instrument, and therefore there's global interest in developing instrumentation that will further the scientific case of the instrument and further individual research groups around the world. And so there's a number of instruments and back-end instruments that have been delivered and form part of that back-end processing equipment for the MeerKAT telescope. We participate in things such as the SETI program, called the Breakthrough Listen program, and really what's happening there is as MeerKAT is busy doing its science, it also collects data for the SETI program. And for those of you unfamiliar with the SETI program, it's the search for extraterrestrial intelligence. So looking for artificial radio signals from interstellar space. The number of other international projects we're involved in, and of course, really very close to our heart, is the African VLBI network, which is really about establishing radio astronomy infrastructure and capacity across the African continent. I spoke earlier about that strategic advantage that the African continent has for supporting research infrastructure such as radio telescopes. And the African VLBI network and the activities around that, so it's not just the infrastructure, it's the capacity, it's identifying the opportunities, developing the skills, etc. It really is a substantial opportunity, and I think it's a really strategically important program for SAREA. There's the Hero telescope, because we've been able to establish the site and establish the infrastructure. What it's done is it's enabled other organizations around the world to locate their scientific instruments in the Karoo. One example here is Hero. It's a $16 million experiment funded by our international partners to really study the very first stars and galaxies that turned on at near the birth of the universe. And this, of course, the construction of this involved local suppliers, local contractors in the communities around the MeerKAT and Hero radio telescopes. Other projects such as HIRAX, which is a relatively new project, which is an exciting project as well. Of course, this all is forming part of the Africa program, which really has three pillars. One pillar around human capital development and skills development, the second pillar about development of research and technology infrastructure, and the third around development partnerships, and really strengthening scientific and engineering collaboration across Southern Africa. I think that poses huge amounts of opportunity, and you can only do better and you can only produce better science if we do things together and we collaborate together. And I think that's really an extremely important pillar of this Africa program. There are a few new initiatives in the African program that we're busy exploring. One of them is called the African Co-location Program, where we're starting to look at the co-location of ground stations with radio astronomy infrastructure. And this provides a number of opportunities through co-located science and education programs, co-locating of things such as Comrade, that passive radar system. So there's huge amounts of opportunities here, and we're busy deploying our first instance of a co-located program in Ghana. And of course, the interferometry training network as well, which is a program that we're busy trying to look at to see how best to deploy. So that brings me to the end of this presentation. I'm not sure if I went over time or not, but it's really been an absolute pleasure to be here, and welcome any kinds of questions from the floor. So thank you very much.
Okay, thank you, Adrian, for that very, very comprehensive talk. And I think it's essential that people see the human capital aspect of it, which is very important. There was nothing in Carnarvon, and if you go there now, you cannot believe the transformation. So, colleagues, I will open the floor for questions, but just before that, I just want to acknowledge the presence of someone whom I don't personally know, but Adrian could shed more light, and that is Dr. Bernard van der Rohe, who was instrumental in getting SKA bid to South Africa, PhD at Cambridge, worked in the office of President Nelson Mandela. Need I say more? Things are named after him in the scientific community. So I just wanted to acknowledge that he's attending this talk. So thank you very much, Professor van der Rohe. So what I'll do is I'll open the floor for questions. You're welcome to type something in the chat, or you can just put your hand up, and then we'll take a few questions. So while people are pondering about questions, Adrian, maybe just give us an indication of the costs of SKA phase 1 and 2. So what are we talking about here? 10 billion or 5 billion euros? What numbers? I know they fluctuate.
Sure. For SKA phase 1, for the construction of SKA phase 1, the current budget is of the order of 1 billion euros. For phase 2, I would probably be hesitant to put a number because no one's really revised the costing for phase 2. A lot of the detailed design work has been done in terms of costing, from a costing perspective, has really been phase 1 has been the focus. If I was to hazard a guess, and I certainly would not want to be quoted on this number at all, you'd probably look at a couple billion euros, which I think is, it's of the order of a large hadron collider at CERN, for example. It really is it's a mammoth project. But the fantastic thing about building a radio telescope, unlike building the Large Hadron Collider in CERN, where you have to finish digging the tunnel and putting everything in place before you can turn it on, the fantastic thing about building a radio telescope is it's scalable. And so, if you don't have 3 billion, but you maybe have another billion euros, then you can just scale the telescope out and you continue building it out and building it out. It's one of the fantastic things about building an array of radio telescopes. It's just, it continuously can rejuvenate itself. And as it rejuvenates itself, it improves its performance, improves its sensitivity, and improves its scientific return.
Okay, thank you, Adrian. We have a question here in the chat from Roy saying, what is the general status of SKA implementation in the 9 African partner countries, just in general terms?
Sure. I mentioned earlier that the SKA was being delivered in a phased approach. So the first phase of the SKA is really approximately 133 plus 64 dishes, 197 dishes, which will expand on the current MeerKAT radio telescope, so really just located within the Karoo. At the same time, however, of course, we are working through the Africa program with all of the African partner countries, and so the deployment of, for example, the African VLBI network, the development of collaborations and partnerships, and the human capital to support radio astronomy in each of our African partner countries, I think is where a lot of development is happening and a lot of progress is happening. I mean, it's absolutely fantastic that we're participating in this kind of forum now, engaging with colleagues in Botswana, and we've had similar kinds of, with similar kinds of potential engagements in our other African partner countries. It's been really fantastic. We've just almost completed with the first of the telescope conversion projects as part of the ABN project in Ghana. And that's been quite successful. And so, it's looking forward to SKA phase 2. As SKA phase 1 rolls out, we're also going to learn lots of things, and that's going to inform the design for SKA phase 2. So we'll probably see, as part of what's called the observatory development plan, towards the end of SKA phase 1 construction, we'll really start to see, okay, now what is SKA phase 2 going to look like? Are there any things that we can learn from SKA phase 1 that we can now implement for SKA phase 2 and really make this a remarkable instrument?
Okay, thank you, Adrian. I see someone has their hand up. It's Rapelang Simon. So Simon, you can unmute and ask your question.
Thank you so much for the nice presentation. I hope I'm audible that side.
Yes, perfectly.
Thank you. Yes, I just have 2 questions. There are those who are suggesting that altering the orbits of the Earth or Moon can help to solve the climate change problem. What is your view on this, as you are the people who are looking out there? Number 2, number 2 is that the recent Chinese satellite seemed difficult to track by different observatories. What was the limitation of the SKA telescopes in assisting in the tracking of this satellite? Thank you.
Right. So I'll try to tackle that, but I don't think you're going to be satisfied with my answers entirely. So with respect to your first question, I'm quite lucky to have seen the newspaper article alluding to, I think, a senator asking about changing of the Earth's orbit. That really won't have any impact. If climate change is a man-made, should I say, accelerated climate change on the scale and the precedent that we've seen over the last 50 or 100 years, is really a man-made, it's an anthropogenic impact. It's from man-made sources, and so adjusting the orbit of the Moon, I don't think, and I can't see how it would be able to arrest the current climate change trends at all. In respect of tracking of the Chinese satellite that was falling out of orbit, we weren't particularly involved in that. I don't think there was any kind of communication with us or engagement with us to try to track that. One of the potential limitations, and I'm not quite sure how fast that satellite would be falling out of orbit, is that a radio telescope is designed to track sources in the sky, and those sources are generally moving quite slowly. They're not designed to slew very quickly across the sky to try to track satellites. And so that could potentially be one of the limitations in general on radio telescopes, is they're not designed to move that quickly. But in respect of the SKA telescopes, they haven't really been directly involved in trying to monitor that falling out of orbit of the Chinese satellite.
Okay, thank you, Adrian. There's another one in the chat. Thank you, Dr. Simon. Nice to see you at our talk as well. Then we have a question about what are the current plans for the AVN in various partner countries.
So we're busy trying to finish off the first project in Ghana, so the Ghana Radio Astronomy Observatory. I think it was launched by the president in 2018, or I might have that year wrong, which somewhere around there, I believe. So we still have some engineering work to do on that. One of the limitations at this point in time has really been COVID, and our ability to kind of actually move into partner countries. So a lot of the work at this point in time has been around engaging with partners in the various countries and looking at identifying the best strategy forward in respect of development of radio astronomy infrastructure. So there are a number of plans, but we really are waiting for COVID to really subside before we really start solidifying those plans.
Okay, thank you, Adrian. Are there any other questions, colleagues?
I think I see.
Yes, there's one from Zechariah Mishanda. That's Zeki. He's a mathematician specializing in topology. So this could be a scary question. Zeki, over to you.
No, it might be the easiest question of the night. I have two. The first one, by the way, thanks very much for the interesting talk. At the beginning, you mentioned that dark matter can't be seen. We can't see it. So my first question is on terminology. Why is it called dark if we can't see it? Is the choice a good one, the choice of the term? Then the second question is about the progress made so far. The topic of your presentation is search for the origins of the universe. Are there certain indications which suggested we can answer these fundamental questions about the origin of the universe? Has the SKA made some advances which indicate that we are getting there?
Okay, great. So to answer your first question, I hadn't really given it thought before, right? I mean, one of the interesting things is, yes, we can't see it. We don't quite know what it is. And we're trying to explore and use radio telescopes to really, and we're treating the universe as this giant laboratory. And we're using radio telescopes to observe that laboratory, to understand what this matter is. And I almost liken it to, in some cases, many of the experiments that are taking place within the Large Hadron Collider at CERN, etc., are really also trying to answer those kind of fundamental questions about what the nature of this kind of matter is. So whether dark matter is a good term or whether someone should come up with something else, yeah, that's quite a philosophical question, which we could probably have a long discussion about.
Yeah, of course.
But you know what? It's a term that's it's stuck within literature. So maybe trying to change it now might not be a great idea.
Yeah, of course. I didn't really expect a quick answer to that. Yeah. It just crossed my mind, and when I thought about it, I thought my question would kind of appear as a joke.
No, I didn't take it too seriously. Don't worry. But in respect to your second question, I think what is really remarkable at this point in time is that the MeerKAT as a precursor to the SKA is not just an engineering and technology precursor. It's a scientific precursor. And I think much of the science that is being done with the MeerKAT is, starting to probe that question about the origins and the evolution of the universe and the stars and galaxies. And frankly, there's so much data that's being produced and not enough scientists to process all of the data. So there's a huge amount of opportunity. I mean, there's so much data that's become available that there's a huge amount of opportunity for students and researchers around the world to actually maybe start scratching at the surface and understanding, getting and discovering the clues to the origins of the universe. But certainly I think when we start building out on MeerKAT, projects like Hera and Hyrax, for example, also start to probe that question of how did the universe and galaxies and stars evolve. So there certainly are clues that we will be able to answer the question. We haven't answered it yet, but it's certainly something we expect to be able to answer with the SKA.
Okay, thank you, Adrian. So thank you, Zeki. I'm sure we could spend all night, and thank you for your time. And I'm sure you've been in Zoom meetings since 6 this morning until the end of this, because that's the new normal. But thank you so much, Adrian. We appreciate it so much. And I would just want to ask our permanent secretary, is Dr. Nelson Torto, to say a few closing remarks, just to mention to you that the ministry is extremely supportive of the astronomy endeavors, particularly ABN in Botswana. And Professor Torto was actually at Rhodes University when the bid was awarded to South Africa, and he said they enjoyed a glass of champagne. So he's very much aware of these noises and so on. So Prof. Torto, I'll hand over to you to say a few closing remarks, and then thereafter we'll just say goodbye. We can show ourselves in the video just for the record. So over to you, Prof.
Thank you very much, Gregory. I hope you'll appreciate the background that I've been able to put up so that I can look like I'm one of you guys in terms of my understanding of the subject matter. It's really a pleasure to be part of this. I'm always very excited by the SKA, and clearly, I think you were right in terms of the old good memories when I was at Rhodes, because I knew that the Rhodes team was part of the bidding team, and they really played a big role in terms of the fact that South Africa ended up being the host of this huge and beneficial project for the African continent. So really, when you talk about the SKA, I always want to be involved, and I'm very grateful to be used for inviting me, because this is the second of the seminar series that have come along, and I've been able to participate. The whole aspect of the square kilometer array is very unique. And I like the two connections between what the VC said and also what Adrian said in terms of his presentation. I think the concept of the universe is a concept that is very, very special, in the sense that the universe is presented to us as a single entity. And it really, for me, is a new and big thing in terms of how we should look at science, from someone who works for government, from someone who needs to see that problems for society are addressed. The universe is intact, it's a unit. And of course, it means that when we approach all the problems that we want to address from a scientific perspective, we want to address them in a unit perspective. In that respect is that we want to approach everything that we do in a transdisciplinary manner. And it is very clear from what you have been presenting that there are a lot of benefits that have come out of this project, many that could have not been predicted on the basis of the science of the discipline. So the transdisciplinarity, I think it's something that is very key, because we know that even though Africa has got a youth dividend and all the like, we have got issues regarding employment. We have got unemployment. Unemployment is a big thing. And of course, COVID has made it worse. And we are actually experiencing unemployment at the highest level than we have ever anticipated. So a project of this type is a project that really demonstrates that if we were to come up with projects that are transdisciplinary, and that I mean that we are working within discipline, we are working across disciplines, we are working beyond disciplines, where we are applying ourselves to try and find solutions. I mean, the things that you guys are doing are very unique. So let me just say thank you very much, Adrian, for your presentation. And I also want to thank Professor Totolo and his team at BUST for them to be part of this, clearly because of the fact that We, as the Ministry of Tertiary Education, Research and Science and Technology, we have been given the mandate to transform Botswana on the basis of knowledge. And there's no knowledge that doesn't derive its strength from data. There's no data that doesn't come on the basis of science. So clearly what you guys are doing are the essential steps that can begin to deliver for the society in many different ways. And I think the other good advantage of actually looking at issues in a transdisciplinary way is that we work with the people. We don't work for the people. We are not the ones that dictate. We begin to understand how the communities are needing the science that can begin to deliver for them. And the fact that we can work with them, I think is very key in the sense that we begin to be part of one unit. And as you said at the beginning, Adrian, the universe, I think to me, is unique in the sense that it begins to tell us that we shouldn't fragment our efforts. So I'm very, very, very appreciative of your efforts. I'm very appreciative of the collaboration, amongst all the African countries, all the way to Ghana in terms of the SKA. And as far as we are concerned, as the ministry, as Gregory has said, we have a deep love for the SKA, and we are prepared to support, be used to as far as they can go, as far as we can afford in terms of the finances that we have. So colleagues, it has been a very, very special occasion as far as I'm concerned. I'm looking forward to hearing more on these endeavors, and you should count on the government of Botswana in terms of supporting you in your efforts. So with those few words, I want to thank you very much, and I want to encourage you to do more because the continent needs science, and science needs to deliver for its own people, because we want to find solutions that can begin to address issues that are of concern to the continent. So with those few words, I want to thank you again, Adrian. I want to thank you, Gregory, for facilitating. I want to thank everyone who has found time to join this seminar today. I know that there are others that are coming. If I miss them, please do know that it's not because of the fact that I'm not interested, but we have got a keen interest in this. And therefore, I'm urging Professor Totolo and his team to go and take advantage of all this that comes so that Botswana can benefit. Have a good night, and thank you very much.
Thank you for your kind words, Prof. Toto, who's an esteemed chemist, so he's not just an administrator. I know deep down he's a scientist, and he's jealous of all the science we are doing.
Absolutely, Gregor, absolutely,
yeah.
absolutely.
Thank you, Prof, so much. Thank you, Adrian, once again. Colleagues, thank you so much. We've had people from all over the world. I even see my friends from Botswana attending. So thank you so much, colleagues. Have a good evening. If you want to unveil yourself so we can just see who's who, if someone wants to take a screenshot, I'm not so good at these things. There's Bruce from WITS. Nice to see you, Bruce. And there's Prof. Totolo, Gian from the astronomic. There's Haniso and Professor Ogu, Professor Shemang, and Tabiso. Thank you so much, colleagues. And there's Retief, who I used to be at Stellenbosch with. Retief, good om jou te sien. Mar Thomas, wonderful. Professor Modisi from UB, Simon, we're on the board together. Radiation protection, good to see you, Simon. And colleagues, thank you so much, and wishing you a good evening. Thank you very much.
Thank you.
Thank you. Okay.
Yeah.
Good night. Thank you, Adrian.
Good night. Bye.
Thank you, Adrian.
Bye.
Thank you, Mike.
Bye. Bye.
Good evening, Mike. Enjoy the tennis.
Oh, thank you.
Bye, Adrian, and thank you.